Feedback control systems are both fascinating and mysterious. They come in a variety of styles. Here we see a movie clip of the collapse of the Tacoma Narrows Bridge in 1940. A steady 40 miles per hour wind induced natural frequency vibrations into the suspension bridge, which had 8 feet high steel stiffening girders on either side. The result? An unintentional full-scale experiment which gave feedback for a costly redesign and construction of a new bridge. In this book, we do not study this style of feedback control systems. Instead, we study automatic machine-type feedback control systems. Here is a fascinating movie clip of such a system. This feedback control system takes a weighted pendulum, which is stable only when hanging down, and forces it into an upright and unstable position. There it is kept balanced by the feedback control system, even in the face of disturbances. How do such systems work? Well, this book takes the mystery out of automated feedback control systems. It teaches you how to design these systems in a systematic, step-by-step manner. We start with the basic mathematical building blocks of electrical, mechanical, fluid, and thermal systems. Next, we show you how to use these building blocks to construct mathematical models of complex real-life systems. We start with easy models and give you lots of practice problems with work solutions. Then we move to harder models and give you more practice. There are many quizzes so you can test your understanding of each topic. To help you learn even faster, we provide many computer-based interactive simulators. These simulators are embedded right into the pages of this book. You will use them to conduct experiments that show you how math models respond to step inputs and to sinusoidal inputs. Once you've learned these basics, you'll start learning how to design feedback control systems. We'll use popular type of feedback controller called PID. It's an abbreviation for proportional, integral, and derivative control. We'll go slowly through the design process. First, we'll build a math model for a plant and test it in steady and dynamic conditions. We call this open loop testing. Then we'll begin design of a closed-loop controller. As a first step, we start with a simple proportional controller. We show you how to set the proportional gain using a computer-enhanced design tool called a root locus plotter. Then we test the controller with a simplified model of the plant. In the next step, we create a closed-loop controller by combining proportional and integral controls. Again, we set the gains with a root locus plotter, then we test it controlling the plant. Finally, we create a closed-loop controller by combining proportional, integral, and derivative controls. We set the gain with the root locus plotter and test it controlling the plant. I hope you enjoy this book. Visit our website and give us feedback.